we say what we did yesterday. I gave you the basic axioms of hydrodynamics and how one might sort of find all structural solutions to them by using this adiabaticity equation. So there were three key things I wanted to say from yesterday. Which one was this adiabaticity equation, which I'll write as skip these indices for now. Where this delta is positive. Second, we said there exist 8 classes of solutions. And third, we said for two of these classes, there exists an action principle so Lagrangian is a function of a reference vector and physical coordinate mapped from some world volume to target space where the fluid lives, such that physical fluid data is given by the push forward of this vector. And the picture we had was that here is some world volume with some rigid structure, and here is a physical space-time. It's a metric g mu nu and coordinates x mu, which are functions of sigma, and the dynamical degrees of freedom of this Lagrangian system are x mu. Beta is some fixed fiducial vector that you get to pick. Okay, so that's what we got to yesterday, and we saw that this Lagrangian system has this as an identity, as like a Bianchi identity from diffeomorphism symmetries, but the equations of motion of this Lagrangian system are conservation equations, precisely energy momentum conservation equations.
So these two classes are the dissipationless classes?
Yes, they're the dissipationless classes, and of these 8 classes, I should say here that 7 are non-dissipative, what we call adiabatic, and one class is dissipative. Okay. Now, so that's an important caveat, because you see, we have a Lagrangian system. It does what we sort of need to. It sort of captures part of the data, but it seems not to capture 5 of the non-dissipative classes. There's no reason why it shouldn't, because they are anything which doesn't have dissipation is by construction a conservative system. So why isn't there a Lagrangian which doesn't capture these guys? Okay. Now, what I'm about to tell you came from a bunch of empirics, and then I'll try to justify where those. So I'll tell you something we did initially, which was just empirically see what was inadequate here and how to fix it. And we knew certain things that helped us along the way. But then I'll use that as a stepping stone to motivate a different structure, which will derive those empirics from a slightly different set of axioms. Just call it beta A is fine. Yeah.
Okay, so
yeah.
So there's something like a body fixed fluid velocity versus the real.
Something like that. So just to be clear, so the beta vector is not quite the velocity, it's a velocity divided by temperature. So it has a norm, unlike the velocity, which is which is unit norm. The way to think about this is that beta velocity, the fluid is here. So physical configuration of the fluid, you give me some metric, it has some local value of beta, which is the solution. Now, the problem is that beta itself can't be a so you could so instead of writing this Lagrangian, you could have written on a space-time Lagrangian, which is a function of g mu u and beta. You take beta as a vector field and just write everything that you can with derivatives and so on. Leading term will be the pressure term, then you'll have corrections involving shear squared or things like that. The trouble with such Lagrangians is that beta is not the full dynamical variable. Only part of beta is a dynamical variable, and that's roughly clear because you see the dynamics of the system has to be precisely energy momentum conservation. It can be no more and no less. Usually energy momentum conservation is less than equations of motion, but here I want to precisely get it on the nose, which means that somehow there should be a system for which diffeomorphisms in this space are physical, are the Euler-Lagrange variations of the fundamental fields. When I Euler-Lagrange vary my fields, they should vary as diffeomorphism elements.
So you are saying that the energy momentum conservation equation
should be the only dynamical content of Euler-Lagrange variation. It should not be anything else. The way to ensure that is to make x mu's dynamical. Since they're functions of, so just think of this in the D-brain language.
Yes.
Right. In the D-brain language, this is a space filling D-brain.
Yes.
X mu's have the right kind of shift symmetries, so that x mu shifts are diffeos. So when you vary x mu in the Lagrangian, you're actually doing a diffeo in target space. So equation of motion will just be target space energy momentum conservation. Okay. So but I have to do something. So I can't do arbitrary diffeos because I still have to fix this vector beta. So in some sense, this fixing beta here on the world volume of the D-brain is roughly speaking fixing a frame choice. Okay. In some sense, you take this vector beta, it's varying from in space time. Lump all that variation into x mu and make beta some fiducial vector which you can.
That is possible because of counting matches.
Counting matches, exactly. Counting matches because they're exactly d degrees of freedom in x mu, and I'm just fixing a local frame choice. Just make
So u mu by itself would have had one guess, but you are doing u mu by
t.
So you got
Right. So instead of working with the usual variables which where you split up the scalar part and the norm-free vector part, I do this. One reason to work with this variable is that it sort of makes this covariance a bit nicer. But secondly, this is also much more natural, as I explained yesterday, from equilibrium. This vector is really the killing field in equilibrium. Okay, so this is where we got to yesterday. So now I just started asking a question. What about the 5 remaining non-dissipative classes? Why don't they have actions? Why couldn't we just write down these actions? Why didn't this system give us those classes as well? I can prove to you it doesn't, because I can construct the system abstractly, construct all possible energy momentum tensors that come out of it, and check that none of those match those other classes that I have. It's just structurally not possible. So what gives? So this is some empirical observations. So a Lagrangian formulation is possible if I don't work with one copy of x mu, but with 2. Okay. In some sense, you can think of, let's go the other way. can think of two copies of target space, a left and a right, and the beta sort of sitting in the middle. And I'm drawing this intentionally this way to indicate something that is familiar to us from some other context, and I'll tell you what. And you can have two sets of matrix, etc., etc. And in this extended class, we were able to write actions. Okay, so the historically what happened was we were able to write actions in this extended class for a subset of the 7. In fact, that we did even before we did the classification for 12th anomalies for fluid systems which have currents coming from global symmetries that have 12th anomalies. Okay, so people had tried before to write down actions for systems with 12th anomalies, and they couldn't do it, but we were able to do it with this. Now the advantage, so again, it was empirically constructed, but the one nice thing about anomalies is that the structure of anomalies is so rigid that we didn't have leeway. Once something worked, you can try to fiddle around with it and realize that nothing else will work. Okay, so I won't go into the details because that will just take us into a completely different song and dance. But if you take my word for it, there exists a structure in the context of anomalies, which we then quickly learned that we can soup this up here.
Just earlier, your action is going to be written as a function of those variables?
These variables, x mu's are the physical fields.
No, yeah, but the integral will be over sigma.
Over sigma. Yeah, yeah. Integral will be over sigma.
And so you're going to write your action in terms of the matrix of that space?
Which is the pullback metric, which is g mu nu dad. It's like
and beta.
And beta.
And the only dependence on x will be through the metric.
Correct.
That's why conservation of the stress test will be.
Exactly. So and to just to give you a preview of where we are going later. So for a space filling D-brane, because you want full space-time diffuse, the only thing that action can depend on is on the metric. We cannot have functions of x mu. If you have higher codimension objects, like for example, for those of you who were at the colloquium the other day, Brownian particles, then you can have potentials. Okay, space filling objects are special. You don't admit potentials on space filling objects because they break D-flow invariance.
Yeah, and just to be totally clear, just so that I get it.
Yeah.
So if I vary the action with respect to x mu,
Yes.
I vary it with respect to g mu nu, and then the variation of g mu nu with respect to x mu, which is d mu x mu.
Correct.
Delta x mu.
Correct.
And that first part is going to be identified with the stress tensor.
Yes.
And then the equation of motion is there as a combination of stress tensor by equation by part.
Yes.
Now the first part is like the stress tensor on this world volume.
Yes.
But that is the pullback of the stress tensor in space time.
Yes. Or rather, you take that stress tensor and push it forward. Yes. 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 Yeah, it's the one with upper indices. You push it forward.
Okay.
Yeah. Okay. So now two things. When I say doubling here, I mean something non-trivial with the doubling. In that it's not so much that I'm sort of introducing two sets of variables which are decoupled, but these two sets of variables talk to each other. There's an interaction between the right and left variables in these actions. Okay, this is important. It's not like I take an action of this kind and add to it another action of the same kind with labels left and right. Okay, so the full action. So the Lagrangian system here is roughly. I will say this in words. It's roughly basically it's something like this. TAB, G tilde AB, where G tilde is qualitatively G right minus G left. The pullback of the right metric minus the pullback of the left metric. Okay, so just keep this in mind. I put this in quotes because I have to explain a few more things before I get that there. But that's roughly the qualitative structure of those actions. Okay.
So Schrödinger chemistry looks like this.
Coming, precisely. But so far no dissipation, right? So far nothing that would call for Schwinger help. Right. So as I said, we knew this in the context of anomalies, but there is interaction. And you might say, okay, this structure isn't that good enough. The trouble is, we don't have a rule to forbid when you do doubling,
Many.
there are many things you can write down. And the many things you can write down, you can very quickly infer there are many things that will violate this condition I want to keep. Okay? Not everything anymore is guaranteed to have this equation with positive delta. So entropy is not produced, the system can destroy entropy. So we found a cure for this as well by adding one more term, which I will write like this. By adding to the Lagrangian system a term which is the entropy, the free energy current coupled to a vector field. Okay? And this vector field, again, this was sort of analyzing some consistency conditions. I mean, I know technically how it works, and the only explanation I'm going to give you is a post facto explanation I'm going to give you. I won't even remotely try explaining how was it that we landed upon this structure. Okay? So
this plus the left-right symmetric.
So roughly speaking, these tilde variables are left minus right, or right minus left, if you like, and the t's are left plus right. Okay. So in the language of Schwinger-Keldy, these are the classical objects, these are the quantum objects. And everything, in fact, G tildes, they have a non-trivial transformation under this gauge field. They have some non-trivial gauge transformation. It was all sort of constructed very delicately, and we checked that all the sort of Bezzomino consistency conditions that you would want for these symmetries close. There's an algebra. It's not something that is, just works at the tree level and sort of at one shot and then stops. So, but this is very unsatisfying. So there's a story here, and this symmetry, because this entropy current, so this way you see that the entropy current is the current, the free energy current is the current associated with a gauge symmetry, and we saw yesterday that the entropy came from thermal diffeomorphisms. So the symmetry here is what we call U1T, which if I were to go back in time, I would not call it U1 because it's not abelian. It's a symmetry that comes from diffeos. So it's like a so for those of you who know non-commutative geometry, it's like non-commutative U1. Okay. In fact, there are many similarities with that structure.
Is this gauge field dynamical?
So in this construction, it wasn't. Okay. We only wrote down the linear term, but in
some particular gauge field.
It's some particular gauge field. So we didn't write down its kinetic term. We didn't figure out how its kinetic term works.
I see.
Okay. Okay. So now I'm going to tell you how to explain all this, and then I will tell you that yes, it is dynamical, and there is a kinetic term that we think we know what it is.
But even operationally speaking, what am I supposed to do with this Lagrangian?
Okay.
Am I supposed to vary it with respect to A tilde?
You vary with respect to A tilde and you get n, and you vary with respect to G tilde and you get t.
And so that will give me NA is equal to 0 when I vary with respect to A tilde?
No. So there's some Lagrangian system which you write down as a function of G tilde, beta, and so on. When you vary with respect to A tilde, you pull out NA.
What are the variables with respect to you're supposed to vary that actually? There's X, and
There's
what else? X, the two X's,
The two x's,
and anything else?
and there's a gauge field here, under which the x's are charged.
Under which the gauge field. That is this.
That goes into this.
And the dependency action on this A tilde is just linear?
That's what we could infer from the general considerations.
So now if I compute the Euler-Lagrange equation for A tilde, do I get NA is equal to 0?
You get conservation of it. You get this equation.
I'm not understanding. Where
I didn't tell you I haven't told you what the transformations of G's are.
You have told us where else.
Yes. I haven't told you what the gauge transformations of A's are. Okay. So the A tilde.
Sorry, excuse me. So the path integral variables are xl and xr.
Yes.
What else then?
And A's.
And A's. And the A's.
Which A's? The body fixed.
The body fixed. They only live there, let's say. Yeah. And so sorry, Shaz. The key point is that these G tildes have a very nonlinear dependence on A tilde. Yeah. So I don't want to sort of rehash that because that's not the most illuminating way of saying what's going on.
Yeah.
So I'm going to switch gears. take that as a starting point, as the fact that something worked. We looked for an explanation of why that worked. And Gautam already presaged the answer, which is that this structure is very reminiscent of Schwinger-Keldysh construction. So first I'm going to motivate why Schwinger-Keldysh, and then I'm going to motivate where could this even come from, and then I'll give you the dynamics of A and construct actions. Okay? But stop me now if you have questions on this part. Okay.
So earlier, I mean, this is something that I was asking. In the earlier one, the path integral variable was x mu only.
X mu of sigma, yeah.
X mu of sigma only.
Yeah,
Right?
yeah, yeah. That's right. So now I am extending. Well, I sort of have to because I'm increasing my variables.
But increasing the variables is in any way happening because we have XL as well as XR.
Right.
But in addition, you also have some gauge field on the world.
On the world volume, yes. So let me motivate the Schwinger-Keldysh construction. By saying the following. By making a following observation. So hydrodynamic stress sensors they probe causal response. By definition. And this is very clear, for example, in linear response theory. If you, for example, look at Kubo formulae, it's a retarded Green's function that shows up when you compute viscosity. When you compute higher transport coefficients, second order, third order, and so on, is a corresponding extension of retarded correlators. And the theory of all such causally ordered objects is computed not by conventional Feynman path integral, but by the Schwinger-Keldysh path integral. So what is a Schwinger-Keldysh path integral? It's the same kind of thing that we were talking about the other day, but with one forward-backward contour, where you start with some initial state rho, you evolve it forward, and then you evolve it back after the latest time of interest. In other words, you feel free to take your initial state, you turn on arbitrary time-dependent sources, but the only way you can compute causal correlators is after turning on all the sources at the latest time, you don't ask what the future state is. Because the future state depends on all the sources you could turn on after the latest time of interest. Right? I mean, which is not what we do in a scattering experiment, because in a scattering experiment we send in some initial state, we send in some final state, and we project on those initial and final states. So we know what the initial and final states are. In the Schwinger-Keldysh path integral, we only know what the initial state is. We have no idea what the system will evolve to. And the only way to avoid knowing what it will evolve to is to go back in time to where you started from. And so there are many ways to interpret this, and I'm going to interpret this in an operator language, and hopefully sometime next week we'll sort of write a short paper interpreting this in sort of Hilbert space language, not an operator language, but in quantum mechanics, just to illustrate some of the points I'm making now. Okay, so in the operator language, because there are two legs of this contour, you can think of the legs as being labeled as right and left for obvious reasons, and you can think of the right leg as corresponding to the ket of the density matrix, the left leg as corresponding to the bra of the density matrix. Because the kets evolve forward, the bras evolve back, and then what you do at the latest time of interest is you concatenate the bras and kets with the identity. So this point, which I'm going to call the turning point, is just the insertion of the maximally entangled state unnormalized. It's just the insertion of an identity. So here's the Schwinger-Keldysh generating functional. Where I take my system, evolve it with a unitary with some sources which are labeled in U of JR really. and then u of j L dagger, and then you have the rho I sandwiched between. And there are certain things that are sort of, so now you can compute all response functions, and the kind of response functions they're interested in are the following. So in an action language, this guy starts off its life as a decoupled action for right and left with a source operator coupling which has a relative sign coming from the fact that this has a dagger relative to this guy. Okay. Which means that if I change a basis, to what I will call average difference operators, then this coupling is such that the metric on the space of couplings and operators is light cone like. Average operators coupled to different sources and different sources coupled to average operators. The hydro correlators are the following, are strings of differences but with one average stuck in somewhere. In fact, one average stuck in the latest time. Okay, this is some kind of nested commutator, and you can ask why don't I take all differences? I don't take all differences because a correlation function of all difference operator of any kind is 0. Okay, why is that? So to turn on a difference operator, I just need to turn on an average source. Which means I have to do the same source on the right. I can get away by doing the same source on the right, the same source on the left. Which means that this u, which is evolving me forward, is the same as the u dagger that's evolving me back. And then it's very obvious that z of jj is trace row. So there's nothing to compute because these correlators are 0. The first non-trivial set of correlators are retarded functions, and they are they are the hydrodynamic guys. Okay. So but this is a strong statement that, so we're now going to sort of take the following inspiration. So these are statements that are well known, they're true, you can read them in standard textbooks.
Why are you singling out these guys as hydro?
What I mean is that hydrodynamics, the transport coefficients in hydrodynamics, they come out of only a subset of all Weitmann functions. They don't involve every other Weitmann function. Okay, and in this basis it's just this. Okay.
You know, just a small comment or question about that. You know, what is natural to compute in hydrodynamics? In hydrodynamics, you know how to couple hydrodynamics through, let's say, an external thread. So the kind of question that you can naturally ask is, given a starting state, let's say equilibrium, I turn on an arbitrary stress tensor, and then I measure the stress tensor at a
later time.
And I can turn on the metric in an arbitrary way.
Yeah.
Okay. And so I can compute the response, the stress tensor that I get later in a Taylor series expansion in this metric.
Right.
So this gives me something. Okay, this is clearly some correlation function because you differentiate with respect to many metrics.
With one instance. No.
Okay. Now this, I believe, is what he's talking about, because by turning on this metric, you're working in a particular state, the state that you would get by turning on these ones.
Mm-hmm.
So that's the you know, his thing. That thing you can think of as creating a state.
Yeah.
Sorry,
Yeah, of course.
This creates a state.
Yeah.
This creates the
Conjugate bra.
because it's the same state.
Yeah.
These are just equal.
Yeah.
You're turning on equal operators, and therefore you're turning on whatever different ones.
Right. But then you
And you're
do
measuring
one measurement.
the object,
Yeah.
which is like the sum operator, and therefore the
Yeah. Yeah. The average. Yeah. And you just put in the average here at the very end to prevent this whole thing from collapsing back to a trivial overlap.
So it's an expectation value
Yes.
in the disturbed state
Correct.
of the stress tensor.
Correct.
Exactly.
Correct.
Caused by that.
Yes. Exactly. Exactly.
The others will rise.
Right.
Caused by
Right.
that. It should be
Right.
caused by the external nature.
Right.
So this is really a classical representation
Exactly.
of the expectation.
Right. Because really the hydrodynamic stress tensor that we talk about
Yeah.
is the one-point function in an external medium in the source, with the source turned on.
Right.
Yeah. You should think of it, each of these lines as the representation of the state that you get
Yeah.
by turning on your source.
Right.
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 And in that state you're computing, as you said.
Right. Right. And to just say what Shiraz said earlier, the constitutive relation that you write down when you take the hydrodynamic energy momentum tensor and expand it in terms of the ideal fluid, viscous term, second order term, third order term, are just capturing the moments of this one-point function. So they just pick out higher and higher correlators of the energy momentum tensor with itself. Okay. So
And you could put two of them, two of these three average values, then it will give you the correlator.
it will give you correlators. Yes.
And that you don't know how to compute directly.
Yes.
Ah.
That's not part of classical hydrodynamics.
Quantum.
Yeah.
That's right. Yes. Right. But they will be relevant for what we're going to say.
The only thing, if you try to put the only correlation function that's directly computed from hydrodynamics
Are this exactly. Yeah. 1 point function.
because this is what you can do.
Yeah.
Make a name.
Right. Right. Very good. So we have these statements. Now let's think of this problem in the following way, just to sort of get some orientation.
And just, what always confuses me about this discussion is the sign. I mean, I know there's a relative sign, but the absolute sign also confuses. Like when you say this is P difference,
Yeah.
that's because you turned on G upper and G lower same.
Same.
So what about the fact that dP is positive this way and dT is negative that way? That you don't take.
That's the taken into account in going to this light cone basis.
It's always confusing.
Okay. Hey, I'll tell you. I'll tell you this in a fashion that's cleanest.
Okay.
If you really think of this as coordinates
Hmm.
in a two-dimensional space,
These are like this.
these are light cone coordinates.
Yeah, it's just when the metric is time like or space like.
No, but this is not the physical metric. This is the metric in operator space. Right. Right. Okay. Good. So imagine that this was your. So we want to sort of do this problem, but we want to sort of do this problem. This is all fine if you knew, and you could go through this exercise if you knew what the microscopic theory was, what the microscopic phi's were. And it's only true in the microscopic theory that this action is factorized. It's a right minus left action. Because that's how in terms of the fundamental field that I've used to build rho I, that's where it's true. That's how I set up the problem. But hydrodynamics is not a microscopic question. It's a long wavelength, low energy thing. So I would have said, start with this problem, and then you integrate out stuff which are irrelevant in the hydrodynamic medium. All the stuff that's happening around, which is not going to survive to the long wavelength. Sounds good, but you have a problem. The problem that we just saw there, which is the following. So you can do RG on these guys. So of course there's a piece here which will be the low energy modes of phi r and phi left. They will be factorized. But if you go back to this problem and look at what the phi right phi left correlator is, or what the phi right phi left Green's function is, this is a non-zero Green's function. Which means you're guaranteed to get interaction terms in the low energy. So if I do RG here, I'll get something which couples the low energy phi right phi left degrees of freedom.
Less is the slow variable.
It's just a slow variable. So you're just doing Born-Oppenheimer, RG, whatever you want on the full system, and you're writing down the effective action for slow variables, but the effective action now has a new piece. And this piece governs everything. It's the same piece that we saw here. There were interactions between them. And so if if you don't constrain this piece properly, you're not guaranteed to get the right low energy theory. Okay? In other words, this piece, which we called influence functionals after Feynman and Vernon, who were the first to sort of talk about these kind of terms, is really responsible for telling you how the relevant degrees of freedom in the hydrodynamic limit survive. They control pretty much all the dynamics. This is the sort of boring part of the low energy theory. Okay. So you'd like to ask, how do you constrain these guys? And to do that, we are going to take this as a guiding principle. And what we're going to do is basically try to infer some symmetries from this functional integral that are suitably robust, so that when we do this RG flow, we are guaranteed to have constraints placed on this guy. Okay? So the logic is very simple. Identify the maximal symmetry set that, in addition to the usual Wilsonian naturalness that you would use to write down such terms, further constrains it so that you don't get junk.
So just to, I mean, this I think I have asked Loga infinite number of times, and maybe you also.
Yeah.
So this, in the microscopic theory, that one sitting there
Yeah.
is like a delta functional sitting there between phi r and phi l.
Correct. It's roughly the piece that you can use to think of as a trace.
Right.
Right.
Exactly. The trace.
Yeah.
So that's the coupling. I mean, that will give me a phi r, phi l kind of propagator in
Correct.
the theory.
Correct.
And that's becoming this influence function.
Correct. Correct. Exactly.
And you also have coupling through there.
Through here?
Yeah.
Well, in general, yes. In fact, in the thermal case that I will discuss in a second, the coupling that's also nicely constrained. Right. You're completely right. So you're right that there are correlations built in the initial state between the right and left, because if you like, it was a density operator.
But that one is what? I mean, isn't it something plus or something?
No, it's a density operator, right? Just think of the entanglement in the density operator.
But
To the right.
if you were infinite temperature, it would have nothing in here.
Identity. Yeah. Exactly. The infinite temperature contour is simple. It's just another. Yeah. That's the nicest theory. Good. Okay. So now I'm going to make a series of claims. So I'm going to call this star. I'm going to call this the topological limit of the Schwinger-Keldysh functional integral. And it follows from existence of a BRST SUSY that acts on the system. So claim is that there exists some BRST operators, QSK, Q bar SK, such that these difference operators are Q bar exact. And I will just say it in the following way. That there's an algebra acting on the space of operators, Schwinger-Keldysh operators, which came with a doubling, which came with two labels, right and left. I just basis changed into right plus left and right minus left. But on that there's a bigger there's an extension of that algebra on which two more operators act, which are just Grassmann odd nilpotent operators, Q sk, Q bar sk is squared to 0, and in fact they have a 0 anti-commutator. But what they do is they take the average operator and make it a ghost-like operator or an anti-ghost-like operator, and then they take this ghost and anti-ghost and bring them down to difference operator.
So the idea is to understand the star equation as a one identity of some
H. No, right now, no, just topological supersymmetry. That's right. So far, just topological supersymmetry.
And the O guys,
Yeah.
they have a meaning in the coincidence theory also.
They have a meaning in the fine-grained theory. There will be coarse-grained O rights and O lefts. But Qs have universal meaning. Qs are topological. So Qs are, in some sense, we're going to say, are blind to the RG. So statement that would have to be, if there was an O right minus O left parent operator, its RG flow would also have to be in the BRST cohomology. That's the constraint we're going to employ. Okay? Now, we like to propose that there are two Qs, a Q and a Q bar. There's relative CPT conjugates. The folks at MIT, Hong Liu and his collaborators Crossley and Glorioso, they also recognize that this statement would be true had there been a supersymmetry, and posit a supersymmetry except they only want one supercharge, only one Q, no CPT conjugate. Okay? At this point, that's the only difference.
So how does this diamond work out?
For them, their diamond is sort of broken up. This goes to here and this goes to here. You think of, erase those lines. So you have two different multiplets. Okay. Okay. I can tell you lots about just this structure, but let me add one more element to this structure. Okay. This structure, I claim, is generic to any density matrix. Any Schwinger-Keldysh construction has this feature. Nothing about I don't have to say anything about what row I was.
I presume that part of the motivation of doing this is to make something that is pure difference to exact.
Correct.
But you don't seem to have distinguished between pure difference and pure sum here. Is that right?
What do you mean?
Sorry, maybe I'm mistaking this, but if I interchange Q and Q bar and difference and sum, I get the same structure?
No, but if you interchange Q and Q bar, the sum is always the bottom component of the multiplet.
The arrows are always
Oh, I'm starting from down. Sorry.
The flow is always down. So
sorry, I started looking at from
yeah, in n equals 1 chiral language, the difference is always top component. Okay. I'm going to now specialize to thermal density matrices. In which case, the feature that Shiraz mentioned, and we talked about the other day, is that there is a nice structure here because this is rotation in imaginary time. So there's an insertion of the operator e to the minus beta h.
You don't normalize it by dividing by the function.
Let me not do that. I don't have to. Let me not do that. When I compute correlators, I will normalize for now. Let me leave it at this. I don't want to do that for the following reason. When I compute z, rho j, I actually do want to get the partition function, the physical partition function, the generating function of the eigenspectral theory. If I normalize, I'll get one, which. So I think that's just a choice. What you actually want. And okay, there are many ways to say this, so let me say it in two different ways just to convince you that there's something non-trivial. Just as correlators of the difference operators here was 0, there's a new identity which is the following. correlation functions of the right operator at some time minus the left operator at some time minus I beta, and strings of such operators. Okay, this is not the same operator as this. This could be some other operator, but the structure has to be the same as this. These are 0. Okay, if I forgot about the I beta, that's the statement you'd get from here. There's a new statement which comes from this end of the contour. In other words, you see, the reason you got this statement was because there was an identity here. Find that if you do the same thing in the future, you can collapse that piece of the contour till there is something which is different, which also tells you that these difference operators cannot be out of the future. Likewise, there's something closer to the density matrix in the thermal case, that if you take a thermally shifted operator and subtract it from the right guy, you'll again get something trivial.
This is what you told us about the
Yes, this is what I told you about. These are the KMS type relations. So from here you can get the KMS type relations. So it's sort of encoding the KMS relations on.
And it's just the statement that going through the thermal leg is translation right now.
Exactly. So, once you played the game there, you could say, but there's another structure which says that O right plus O left goes via Q KMS, Q bar KMS, goes, anti goes, and then comes down to O right minus O left of T minus I beta.
A new set of goals.
A new set of goals. Well, actually I think the same goes, but I'll tell you why.
But a new set of supersymmetries.
A new set of supersymmetries. New set of supersymmetries and a new set of supersymmetries which are also nilpotent. By construction.
Now there's an infinite set of such things, because then we can pull T minus IN.
Well, if you, okay. Yes, you can index them by an integer. There's a discretum of these charges. Right. You're right. And let me say one thing, and then let me tell you what the algebra is for one charge. You keep your discretum in mind. I'm going to sort of try to avoid the discretum and try to jump to a continuum, which will involve making an assumption. But you will see what that assumption buys us. So first question I should ask is, when my density matrix is thermal, if I have these force charges, are these Q's closed, and do they form a closed algebra, or do they generate other things? Okay, that is an operational question. You should just check what happens. And the claim is the QSK, Q bar SK, Q KMS, Q bar KMS close along with two other operators These four are Grassmann odd operators with ghost numbers plus minus 1. These two are Grassmann even operators with ghost number 0. Okay. And in particular, I'll just write one commutator, one anti-commutator. But if you take a QSK and a Q bar KMS, the relative ghost numbers cancel, so you should get back something bosonic, and what you get back is LKMS, and this looks like a supersymmetry algebra, and LKMS really does translations by I beta in the thermal direction. LKMS is the bosonic operator that takes something and it maps it, it shifts its time argument by I beta. So it does thermal translations. That,
choice.
that's a choice. That's a choice for convergence of the path integral. I don't want to go up. There's a relative ordering here. I can't fudge that.
Ah, yes.
So, okay. Again, the folks at MIT want one Q here. They don't, of course, once they have one, they say this is some Q, this is some Q bar, and then they write an algebra which says Q bar is this. So they would sort of concatenate this into a set of Q bars. They would throw this away, and they would just write this. That's the difference. That's the operational difference.
So in this
What's Q0? Okay, so right now Q0 is something that I am telling you exists for closure of the algebra. And I'm not going to say more than that. I'll try.
Sorry, so, I mean, I can see that you get something roughly like this, provided the two hosts were the same.
Yes.
So that's part of the assumption.
That's part of the assumption. Yes. Okay. There's a stronger assumption we're going to make, which I'm going to tell you now. Okay. Yeah. Okay. Right. Okay. So yes, we're assuming the ghosts are the same. We're assuming the algebra closes on the same set of same multiplet structure, and the intuition for let me give you an intuition for Q0, and I won't say more than that. See, the primary charges in the theory are QSK and Q bar SK, because they are agnostic to the structure of the density matrix. Okay. Then you say, then forget this logic that I gave you. Then you say that there exists LKMS, because when you have thermal density matrices, there is the operation of translating an operator by I beta. Okay. Now the point is that once you have a QSK and a Q bar SK, every operator has to be in a multiplet of 4, which means LKMS has to be in a multiplet of 4. So work backwards, you infer that Q0 KMS, Q bar and Q KMS come from there. Okay. That's an easier way to argue. I mean, the physical way to argue is the word identities. The mathematical ways to argue is take two of these charges given, build this.
There's a diamond of the keys.
This is the diamond of the Qs. Okay.
Just to make sure I understand your methodology.
Yeah.
So suppose I add this Q bar KMS and QS.
Yeah.
On OR plus OS.
Yes.
So that the first action takes me to OG,
Yes.
and then the second action takes me down to OR minus OL because it's just by SK.
Yes.
So on one side I just get OR minus OL
Yeah.
without the shift in beta.
Yes.
If I just do it the other way, I get it with the shift.
Different beta.
But why doesn't the same thing also tell me something similar for Q, SK, and Q? I mean, why is Q and Q bar?
Because you go this way.
Each of them involves
Is
one.
one
I
bar.
see.
Yeah. The easy way to count is ghost number conservation. I mean, two Qs will take you ghost number plus 2.
Yeah.
There's nothing at ghost number plus 2 in the system.
Okay.
Okay. So the couple of things I should say here.
I'm sorry, LKMS by definition is operator minus operator as shifted by action.
Beta. Yes. Sorry. Yes.
Operation.
Yes. Yes. Sorry. Yes. Thank you. I always forget that one, that relative one, and then it's an that's why you can expand this eventually.
It's like a translation.
It's like a translation. Right. Okay. So now let me try to, without getting into technicalities, which we can go into if people are interested, try to give you a feeling for this algebra. And my prototype example is the following. And the labels are sort of suggestive. And yesterday I talked about Lie derivatives for all for a good reason. So let's just say so an analogy, which is actually quite an accurate analogy. So imagine you have a manifold which is doing ordinary differential geometry. I have a manifold in some n dimensions and have the space of p forms for p ranging from 0 to n. On the space of p forms, there is a natural operation that we are all familiar with because you can differentiate forms. There is an exterior derivative. Now, given in addition a vector, there is another operation which basically says take the form and contract the first leg of the form with the vectors index, which will reduce the rank of the form by 1. And once you have these two operations, you can define a third one, which is the Lie derivative of a vector along the form, which will keep the form rank invariant along the vector. Lie derivative is always along some vector. So the Lie derivative along the vector is actually the anti-commutator of the derivative with the interior contraction. Okay. I can say this is a supersymmetry algebra with Lie derivatives being ghost number 0, interior contractions being ghost number -1, and exterior derivative being ghost number +1, which is almost like 1/2 of the structure.
So, by this vector you have some particular filling vectors in mind?
No. So I have something in mind which is the following. Imagine you have a gauge theory. Okay. Let's say M, so there's some B, and
Sorry, between supersymmetric and quantum mechanics, is this the structure that arises? One of the supersymmetries is implemented by M.
yes.
Is another supersymmetry implemented by psi?
Well,
Hamiltonian direction.
it's very similar. It's almost similar. There's a catch that you actually want this to be time translation.
That's right.
But in that particular case, it's actually the same structure. But okay, a better way to say it, which this is the exact analogy of what I'm going to tell you now. When Witten constructed the Donaldson-Witten theory, where he was computing 4 manifold invariants by twisting n equals 2 super Yang-Mills, this is precisely the structure. Because you take n equals 4 supercharges and you twist them, you get 1D. And the Lie derivative will be basically some kind of gauge transformation.
Yeah, actually, you can call it D and then star of D, the Hermitian
Hermitian conjugate. So,
not exactly.
which is not exact. In quantum mechanics, it's not exactly that. Yeah. I think in quantum mechanics, I think it's a bit more.
And then you get the Hamiltonian is like the Laplace.
It's like
Del square.
yes. It's like D, right.
The harmonic.
Right. D star D plus star D D or whatever. So here, think of the manifold as having some gauge structure. So I don't want to use technical language, but let's just say you have some manifold on which you have some symmetry acting. Okay, and then these Lie derivatives, as you were thinking, are the vector fields that generate the symmetry. So they have orbits, but they have horizontal segments, which are gauge orbits, and then then you can take the horizontal segment and sort of drag them up along the gauge directions by the vector fields. So in some sense, the manifold is sectioned by some base spaces, different values of different horizontal sections, and then you can sort of go from one section to the other by doing different amount of gauge transformation.
So the horizontal things are like gauge slices.
Are gauge slices. Right. So this structure is very useful if you want to talk about cohomology of this manifold quotiented by the symmetry action. That is, you want to talk about the cohomology on these gauge slices.
It's in this whole discussion, is zeta necessarily Green vector?
It doesn't have to be. It's just a symmetry generator, direction of symmetry generator.
What do you mean by symmetry generator?
Okay, so what I mean is that the manifold. So I have some manifold, and I have some gauge action on it, and that gives me B. And I want to know what are the elements, the cohomology of M mod G, and the zetas are the elements that take me from a given gauge slice up off the gauge slice. They do. Because you see, I zetas actually do translations up this, sort of push me up that way.
I'm sorry, I missed it. Could you just say again what all is behind the question?
Okay, I'm saying that I have some manifold on which there's a group action.
Yeah.
So I'm looking at the space M mod G.
Yeah.
Okay, and I want to talk about the cohomology of M.
In metric, is there a metric on this manifold or not?
We're just doing cohomology, so no metric.
Okay.
Just a topological structure.
Fine.
And I want to know what are the elements of cohomology of M mod G.
Fine.
So usually you would say, well, if it's all geometric, you would say it's the pieces that are invariant under the G action.
Right.
But let's say this is not a nice space. The G action is singular. It has lots of ugly singularities.
Okay.
So the way to do this is the following. I didn't want to get into this technicality, but I think it's helpful. So instead of looking at cohomology of M mod G, you look at the cohomology of M times the universal G bundle mod G.
Universal G bundle means what?
It's sort of the space on which G acts most naturally. It's a space associated with G itself as an algebra, group elements of G. And roughly speaking, if you think of gauge theories, it's a space of all gauge connections. Okay? And
Not just flat things.
not just flat connections, all connections.
Right.
Okay? Now the point is that EG by construction is a space on which G acts nicely. So EG mod G is a smooth space. Okay? So this is smooth. Which means that when I take the direct product and take the quotient, the singularities in M gets covered up by the smoothness of BG. That's one technical statement. But the other statement that's helpful is the following. EG by itself has no cohomology. EG is contractible. So the space of gauge invariant data, that if you take the space of all connections, and then you quotient by the space of flat connection to sort of get the gauge invariant stuff, there's a natural cohomology on BG which is basically the space of gauge invariant data. That is polynomials of field strengths.
This G is G at each point in space?
It's a G at each point in space. So on
So that's flat connection.
that's flat connection. But here, you can just be purely algebraic. You can just talk about connections and their field strengths, and you can define the D action on EG very simply. It's just the statement that you have connections, and their exterior derivatives give you field strengths.
Right.
Then you can pull out the connections from there by associating every group, every Lie algebra element with one I. So I have if G has some number of generators. For every generator there's an I, and for every generator therefore there's a Lie derivative. In other words, you can think of the space EG, for which this diagram is a bit more appropriate, as BG, which are leaves of some fibration, with vertical sections being given by gauge potentials, and the horizontal data being given by gauge invariant field strengths. Okay? So there's a sort of abstract cohomology argument which you can just do on EG without ever talking about the differentiable structure of the manifold. And then you can take the usual definition of derivatives and on the manifold and put them together. Okay?
I'm getting this roughly 80%. But then you want to make your punchline a little bit.
Good.
So where is M coming in
So again, I started with an M because this is more familiar to us. But so this structure is just true. But how can I use this structure? The structure is most useful. See, the point is, if M is a nice manifold, this is geometric cohomology. You just look at cycles. Right? Just do what you naively do, and you're very happy with it. But suppose M is not defined to you as a nice manifold. It's defined to you as a topological space on which there is some group action. So I just give you some algebraic structure. I'm not giving you any geometry. There nevertheless has to be cohomology. How do you define cohomology when you are only given that algebraic structure? That's the problem this is trying to solve. Okay? It's trying to solve it by doing the following. It says, forget about M for a second. Think about just G. G is a group. It has a Lie algebra. Associated with the group and the Lie algebra is this universal covering, universal space. On that universal space, there's a G quotient, which is this Bg, which is just a space of nice objects that are gauge invariant.
All connection
Modulo gauge actions.
Yeah.
Exactly. And that's a nice space. So let's first talk about cohomology on that space. Clearly, the answer is gauge invariant objects.
That's a nice infinite dimensional space.
This is a nice infinite dimensional space.
So you started with some nice finite dimensional space and you made it some
Right.
problem over to infinite dimensional.
Right. But, this
Okay.
but all I'm saying is this is not unfamiliar because exactly what we do in gauge theories. We just don't use this language. But-
yeah.
but-
we compute the cohomologies of this space and gauge theory.
Well, if
Well, what is that? Okay, yeah.
but we, well, the space of physical actions,
Space of physical.
the gauge invariant physical field strengths,
Yeah.
and that's all this is picking up.
Right, but do we ever compute the cohomologies of that? I never think of the topology of that.
No, but we never do it this way. But if you're doing topological field theories, like what Witten was doing, then the sort of then you do this, and then you fold in the structure on the manifold, and then you get topological information about the manifold. Because you see, use the gauge field as a probe of the manifold structure.
The space of gauge connections is clearly dependent on that.
Right.
Yeah, I mean, I'll have some structure of machine groups.
Exactly.
That will use the probe the cycles again.
Exactly. So I mean, so all of these words that we use in physics, they all make perfect sense if you have cycles, if you have geometric structures. But the whole point of this whole language of equivariant cohomology is the algebraic definition of cohomology in the absence of any geometry. Of course, it agrees with the geometric definition when there is a geometry.
Right. And now this is meant to be an analogy for what, please?
Good. So this is meant to be an analogy. In fact, it's a very precise analogy in the following sense. It's a sort of baby version of this, because this is the n equals 2 theory. This is the n equals 2 topologically twisted theory. I'm going to take this and make it the n equals 4 topologically twisted theory. And D and a D bar become a QSK and a Q bar SK.
Okay.
Lie derivative becomes Lie derivative. And the directions of gauge or gauge transformations, the gauge potentials, the interior contraction become Q KMS, Q bar KMS, and Q0 KMS. Okay, so it's a non-trivial fact that once I double my cohomology generators, I get 3 interior contractions.
And Hong company would have an equal to it.
Hong and company would have an n equals 2 theory. They won't even have this gauge symmetry interpretation. Yes. Clear? Okay. So sorry, this is telegraphic, but hopefully the physical picture here is clear. I don't. I mean, when
I would have thought of homology and just non-contractibility.
Poincare dual.
Circuits and Poincare duality.
Ponc-
So you're okay.
Yeah. Okay.
You know, whenever Ashish would explain black hole counting to us,
Yeah.
whenever we'd ask him a question, he'd say, see, let me give you a simple analogy. Consider fighting.
physical modular form of weight tensor. Okay. So hopefully it wasn't that telegraphic.
Abhish's case, it wasn't just not telegraphic, it was reverse numeric. Understood the backwards difference.
Okay. All right. So I'm going to sort of say all these now for that structure, but I'm going to make manifest some of the things I said here. And what I need to do is I will for a moment be a little bit coy about what gauge symmetry, because it's related to this story here. But let's just take an algebra which has these these 6 generators. Imagine there's a gauge symmetry, and I'll tell you what structure overall there is, and then I'll tell you what the gauge symmetry is.
Wait, so just to understand the logic.
Mm-hmm.
You explained that you need this diagram tells you the field content what you need.
Mm-hmm.
You need one cos
Yeah.
and one anti-cos for every what? For every
Operator.
operator, and the operators are the stress tensor?
Yeah. Well, or in fact, for the full operator algebra, I need to. Yeah.
Or the operators will be the diffeomorph.
Well, in a microscopic theory, just take all the operators of the theory.
They will have that.
They will have
but in your setup,
In our setup, there will be
the diffeomorphism
diffeomorphism, the x mu fields really.
will be the okay. So for every x mu you have a cos. Is it the same? Will the cos carry a mu index?
Yes.
Okay. So for each x mu there's a cos. There are 2 cos, and now you have to what you're supposed to do is to write down an action
Mm-hmm.
and implement the symmetry algebra in a
Yes.
non-Cartesian.
Yes. Exactly.
That's what you're
That's exactly what I'm going to, but I just need to explain the symmetry algebra, and then we are back to business. So if you like, the top guy here was the x right plus x left, mu. The bottom guy is x right minus x left, mu. And then there are goals that go along for the right. Okay. So let me.
And you're going to tell us, just to have a view of where we're going, that this procedure will force us to introduce new gauge.
It will force these symmetries will force us to introduce new gauge fields.
If you want to have the symmetry implemented in Lagrangian, you
Exactly.
need new fields other than the x's.
X's
These
and
will be
new gauge fields
New gauge fields
will be of this general structure. I'm just going to tell you what the structure is.
Right.
So there's a name for this. So if you are looking for what this means, this algebra that there is something that is usually called extended equivariant cohomology algebra. The notion of equivariance is simply the fact that there is a gauge action. It's invariance under gauge. It's covariance under gauge action. So what we're going to have are a set of charges, a Q and a okay. Let me just use the same languages here, a D and a D bar, and for reference to that side of the blackboard, think of them as QSK and Q bar SK. And there's a gauge symmetry that's acting, which is this G. I'm yet to tell you what that is. The gauge sector has interior contractions which I'll call I plus, I minus, and I0, and think of these as QKMS, Q bar KMS, Q0 KMS, and there is the Lie derivative which think of as LKMS.
Good, sorry because
Yeah.
we asked so many questions, but just to say that another talk, we have another talk at 11:30.
Okay.
So
Let me
some time.
yeah. Let me stop soon. Let me just tell you the algebra,
Yeah.
and then I can stop. Now, rather than go through the extended logic of how the algebra is generated, let me just make the following statements. Because there are 2 sets of charges, it's easiest to work in a 2-dimensional superspace. Okay? So this is So natural action on let's say RD/2, and the gauge symmetry, two thetas.
And the reason is it topological, one reason is topological is that there are no spinor indices anywhere.
Correct. Correct. They're just Grassmann, they're just scalar supercharges. Exactly. The gauge sector will have gauge fields in the physical directions, but it also have gauge fields in the theta and theta bar directions. The coordinates of this I will call sigma a and theta bar. But everything is a superfield because every function in superspace has a theta bar expansion. Okay? There's a covariant derivative. One theta and one theta bar. N equals 2 means D/2 means two directions.
You're heading towards n equals 4 or not?
No. Nt equals 2 means 1 theta and 1 theta bar. Okay, let me say it this way. The physical theory where this would come from is n equals 4 superangles, 16 supercharges. But the Waffa-Witten twist of that theory will give only a Q and a Q. Okay. If you do n equals 2 superangles, the Witten twist of that theory will give you only 1 theta. So what I described here is the story for 1 theta, one half of the sector. So the gauge structure is very clear. It's like a usual gauge field, except that now it's a gauge field living in superspace, which means it has these theta and theta bar directions. And think of these guys as roughly corresponding to Q KMS and Q bar KMS, as picking out Q KMS. And then there's one more gauge non-covariant combination, that's Q0 KMS. I can write that down for you. It's basically d theta a theta bar plus d theta bar a theta. So those are the three guys. But then there are lots of field strengths. Because there are three covariant derivatives, you can take covariant derivatives of the gauge potentials. Let's just count for a second what the data is. The data, each of these are superfields, which means each of them have 4 components. So that 12 fields altogether. Okay. 3 of them are these 3 guys. They are gauge potentials. Then there are 5 of them. And they're all here. So just count these last 2 bits. There are 8 of them. 3 of them are gauge potentials. 3 more are field strengths. If you like, F theta theta, F theta bar, and F theta bar. And the remaining 2 are derivatives of field strengths. And you can convince yourself by Bianchi identities that follow from the covariant derivative that complete. That's the full structure here.
So it's like a vector supermultiple.
It's like exactly like a vector supermultiple.
It starts with a W mu and then a field strength.
Exactly. Yeah. So in fact, everything that your usual intuition is, you can just work this through. And this guy has a gauge potential, a physical gauge potential, and then it has fermionic pieces, gauginos, and then it has top component F. Okay? So 12 guys, I've explained this. The only thing I need to explain is what is a symmetry. Now is a good time to stop and leave you in suspense.
I was just going to ask, what is the local symmetry?
Not yet. Not yet. So this is the background gauge structure.
Yeah.
X mu will come on top of that will be the matter sector. Okay? And it will transform in a particular way under this gauge symmetry.
And this, okay, first we should discuss questions.
supersymmetry is BRST.
And whatever left behind will be your variable.
So what we're going to do is construct the topological theory first. That's not hydrodynamics. But the topological theory is completely constrained by the BRST symmetry. Then there's one way to always break topological symmetry, which is to turn on top components. I'm going to come in and physically turn on top components, but the manner, see, think about it the way we said the correlation functions. What are we trying to compute? Almost all difference operators, but one average operator.
Okay.
If it is all difference operators, it's the topological sector. Do exactly what you were saying. Go to the future and just put in one extra source. Okay? So in coming to this theory, topological theory, and deform it just the right way to probe the future insertion of the average energy momentum tensor. But you can't do that arbitrarily because it's given by deformation of a topological field theory. So that structure is completely constrained by the topological sector. But you know, the easy problem is find the topological theory, find the most general topological theory, and then do the deformation.